So hello everyone, my name is Carrie Chen. I'm from Intel and glad to be here for the sustainability track session. So today, the topic is OPEA, Open Platform for Enterprise AI, Sustainability. We would like to share OPEA sustainability, also we call it sustainable GenAI computing with carbon optimization. And Alan Liang will join with me. He will share software reference stakes. And I will be sharing sustainable computing architecture and reference solution in the first half. All right, so OPEA is an ecosystem orchestration framework to integrate the performance GenAI technology and workflows, leading to quicker GenAI adoption and business value. OPEA sustainability has also effectively responds to global energy supply, encounter formidable challenge, particularly regarding carbon emission and energy efficiency. So OPEA vision, what is OPEA vision? Is enable enterprise to develop and deploy GenAI solutions powered by an open ecosystem that deliver on lower carbon and higher energy efficiency through carbon optimization computing to meet scale agility and preparing to share-based kind of method. So we're also preparing for white paper, sharing the best practice and also provide the proven reference solutions to community. So OPEA sustainability accelerates the advancement of carbon-optimized computing paradigm, effectively addressing energy and resource crisis associated with the large-scale AI deployment. So this session detail all stack reference solutions of OPEA sustainability and call for ecosystem collaboration. And in this page, as we described before, OPEA sustainability is sustainable GenAI computing. How are we gonna optimize them? We have to consider not only the infrastructure, hardware side, but also the software side. We have to help our customer, like the end users who is really run their workload on the systems. How are they gonna have the responsibility? How are they gonna realize their carbon awareness? How are we gonna help them to understand the carbon awareness? So up to per workload energy telemetry from here, and which means not only to develop carbon optimized hardware solution, but also consider combined software operation, carbon optimization. So from software side, power and performance, intelligent management, liquid cooling solution, etc. From software side, our end user like applications tenant, VM tenants, encourage them to provide better or optimized software, like or VMs, container software should have lower carbon footprint, and we will help them to understand of that. So we would like to make hardware and software collectively with carbon awareness, then provide better sustainable computing, especially on AI era. So here, from the system level side, as GenAI expect to bring more convenience in human society, however, the complexity of GenAI model and the high demand of computing resource also bring new challenges to the data center. The model usually require a lot of parallel computing power and high-speed data access, right? So in order to meet the needs and how we're gonna fully utilize the potential of GenAI, we expect the rack scale system architecture with its modularity, scalability, efficiency become future development for the data center. Rack scale architecture provides, it's not a new words, but rack scale architecture provides strong support for GenAI application, which means we are looking for application-defined system and rack. So we call it ultra-pooling GenAI rack scale system. So designed for reconfigurable, scalable, sustainable, and secure heterogeneous computing platform. So we need to consider, especially when we want to meet complex GenAI workloads. So application-defined our rack, the module are built based on the minimized pool part, the units. So for example, like our Xeon Plus accelerators part designed for interface and enterprise level inference GPU part. And the GPU parts customized for large scale. So system dynamically combine the parts nodes according to the workload requirements. So it has to be flexible and be able to configurable according to the resource sharing philosophy. So the management system also provides model awareness, workload scheduling based on the scaling law strategy. So we are considering to have the switches, like optical circuit switches, which can help us to do reconfiguration. And it's not new, right? And some of the CSP already have this. So addition, focus on, when we focus on the system design, we consider AI is require more flexible system level design and rack level design. And also addition, focus on, from the system side, the infrastructure side, we also focus on how we're gonna improve the liquid cooling. The advanced liquid cooling solution is also one of the hot topic, how we're gonna use them and implement them. So in this page, we also introduced the new technology we call SuperFlu, a new cooling technology for AI system, especially, it's not only for immersion cooling, but also for water cooling. So with this technology working with lower viscosity dielectric coolant for water replacement at the water cooling side. And with the dielectric coolant, we can consider it's an insurance and also to prevent the water leakage damage to the expensive system. So we all know there is some difficulty for lower viscosity with high specific heat. So that's also one of the development collaboration that we work with the liquid vendor, we work with the ODM partners and the whole ecosystem. So right now, at this time, we already achieved both immersion cooling and cold plate with low viscosity dielectric liquid. We already meet over 1,000 watt TDP. And both of them are single-phased. So there is some of next level engineering detail test data that feel free to contact us for details. So at least we can see the phase 1 is already met, and the next level will become challenge that we need to meet single-phase solutions up to 1,500 watt early next year. So now, there's also some live demo and static demo at the exhibition booth, so you're welcome to take a look. Sorry. So we mentioned earlier looking for the core design of hardware and software. So let's take a look at cloud-native carbon and energy telemetry. So here, we all know cloud-native software and Kubernetes is the trend, and everybody looking for a better resource compulsory. So it leverages open source called Kepler, the Kubernetes-based efficient power level explorer. It's part of Cloud Native CNCF sandbox project. It can be used to measure energy consumption of each device from GPU, CPU, and etc. And also we use machine learning model to estimate the energy consumption at the container level. So if we can measure the container level carbon footprint for each workload, and we can better enhance the energy consumption and help our user to optimize for the carbon footprint perspective. So this approach allows us to track the energy and carbon matrix at various levels, including container namespace and nodes, offering deeper insight and energy consumption of each component in GenAI pipeline. So that's the whole application pipeline. We can monitor and calculate the power usage. And sometimes we consider power, maybe not every single power calculation equals to carbon, because some of the energy are green. So how are we gonna continue to optimize or better utilize our energy? Because we also need to combine from hardware side and software side. So this insight can be leveraged to continue guide for future improvement for power efficiency. And now I will pass the time to Ellen to further OPEA sustainability software stack and use cases.
Hello, everyone. I would like to have a couple minutes to give the deep dive how Intel to achieve that solutions. So this OPEA sustainability solution spans the full stack from hardware to software, and all specifically designed with sustainability in mind. The middle layer compressing backend as the service components such as the DAPR and the service mesh that provides essential backend service as well as metrics and the logs for monitoring purpose. So you can see on the left-hand side, the Carbon optimized application leverages Intel hardware feature to enhance power efficiency for each workload. And you can see the middle right sections that present a closed control loop for cloud-native sustainability that incorporating matrix function, field of function, and the cloud KEDA, such managed container scaling based on sustainability actions. Additionally, the carbon-aware resources in this section, including container runtime features that add or remove resources from each container to improve power efficiency. You can see on the top, the sustainable operator that oversees all carbon-related metrics, making decisions and enforcing action based on our user-defined carbon policies. It communicates with the closed control loop interface to implement this action and ensure sustainable operation across the system. So the OPEA GenAI example was deployed on OpenShift and the OpenShift AI to showcase capabilities of the Power Carbon operator. Several large language model LLM instances are running on the OpenShift AI platform, while other microservices are deployed on OpenShift. Caper exposes power metrics on parameters on and the power carbon operator monitors the power consumption of each service, particularly the large language models. Based on the user-defined policy and the limitations, the operator sets power caps for each LLM instance. So in this example, the LLM used about 45% of power during inference and peaked at 75%. By keeping the power usage at 75%, so we can launch 25% more instances within the same power constraints. So furthermore, by reducing power consumption by 15%, we observed only minimum performance degradation in LLM throughput. So this provides additional flexibility to reduce carbon emission while maintaining efficient performance. And to reduce the carbon footprint, we propose middleware deployment, which automatically generates the optimal deployment configuration for each LLM on the cloud. So it's began by grasping the key characteristics of each LLM, such as the number of the parameters, layers, and teraflops. Next, LLM is profiled under various runtime conditions. And considering factors like libraries, data, precision, and hardware configuration. Using this data, we train a scalability model to predict the best deployment configuration for each LLM launch. So this approach reduces power consumption without compromising performance. All right, call to action. So let's work together to accelerate sustainability GenAI. So please leverage OPEA Sustainability all stacks reference, including hardware and software, and design carbon awareness and the model awareness management, and consider together of the hardware and software resources allocations, utilization, and the detectabilities. All right, thank you.